Hello everyone, welcome back to my channel. In this video I will show you how to calculate the band structure for graphene, and in principle this is quite similar to the band structure calculation of silicon that I showed before. So the first step is to do a cell relaxation calculation to optimize the lattice constant, and then the second step is to do a self-consistency calculation to calculate the ground state, and the third step is to specify the K path and calculate the bands non-self-consistently. And the first step is to plot the bands using P4 vasp. So for the first step, this is the in-car file. We start from scratch, and sometimes for the relaxation calculation, I will set those two arguments here, meaning that we don't save the wave function nor the charge density to the hard disk, and that will save some space if you do a lot of calculations. However, you can also leave these arguments out, and then after the calculation you delete the wave function and the charge distribution file. This is the electronic optimization. We use the Gaussian smearing, that is as usual. And EMX we read from the port card that we have talked before. And for the ionic relaxation, we also use the default, that is the CG algorithm, and we relax both cell and atoms, and maximum 100 steps, and the force criterion threshold is 0.03. Okay. So the port card is actually here, and you can use this line of code to copy it here. Okay. And then for the K point, because graphene is a 2D lattice, we only need more K points in the XY direction, but only one K point in the Z direction. For the postcard, this is the lattice vector, and we have two carbon atoms in one unit cell that is specified here. We can actually verify this by visualizing that in the Vesta. So open Vesta and just drag it here, and you see that this is indeed the graphene structure, separated by some vacuum spacing. Okay. As for the postcard, we get it from the standard distribution of VASP, and it's the PPE functional and carbon postcard. And then we use this line of code to move it here. Okay, and then we can run the calculation. And it has reached the required accuracy. And now the relaxed structure is in count car. We can take a look that it also relaxes the vacuum spacing. This is not what we want. So when we copy the count car to be the postcard of the next steps, we will change that back to 15. Okay, so we just copy it to the second step, change it to postcard, and then we change back the vacuum spacing to be 15. In principle, this is also not necessary unless the vacuum spacing changes too much. So this is the new position file, and then we also copy it to the third step as well. Now for the second step, we increase the K point density to 12 by 12 by 1, and then we need to change the in-car. We start from scratch, and the precision is accurate now, and we also lower the convergence threshold here to make it more precise. I-brain equals -1 and NSW equals 0 means that there's no ionic movement, so this is only a single point self-consistency calculation. Okay, and then we just do the calculation. Okay, now it's done. What we need to do is to copy the charge car to the third step, that is the non-self-consistency calculation. And let's take a look. For the K point, this time we have to specify the K path that we want to plot our band structure along. And in this case, it goes from gamma to K to M to gamma. And this is written in a way that there are 30 points between these two, and 30 points between these two, and 30 points between those two. And they are written in a reciprocal space. And for those high symmetry points, you can refer to my previous video on silicon about how to find the high symmetry points and how to find the coordinates. Basically, you can go to any crystallography server and enter the space group, and then you will find these coordinates. Okay, so this is the K point. And for the in-car, we need to specify I charge equals 11, which means that this is a non-self-consistency calculation, and we read from the previous charge car. So it is also important to copy the charge car here, and everything else is the same except that we also add this argument here, L orbit equals 11, so we calculate the bands projected onto the different atomic orbitals. If you just want to calculate a band structure, this is not necessary, but if you want to know what is the contribution of different atomic orbitals to different bands, you will need to specify this. Okay, so that's it. We can just run the calculation for the third step. Okay, so now it's done. And to visualize it, we can use P for vasp and go to DOS and bands here, yeah. And you see that this is the band for the graphene along gamma, K, M, gamma. And you see here at the Fermi level, there's a Dirac cone here at K, which is as expected. And then because we calculated also the projected band, we can go here, local DOS and bands control, and this carbon, and we can select PZ orbital. And you know that for graphene, the PZ orbital form a pi bond that is delocalized, so this Dirac cone structure should come from the PZ orbital, which is the pi bond. Let's see. So we add new line here, and you see indeed those are the pi bonds, yeah. Then we can see what is the PX and PY orbital here, and we add a new line here. And those are the px and py orbitals. They contribute to the sigma bonds that is away from the Fermi energy. And we can also take a look at the s orbital here and add new line here. And those are the s orbitals. They also contribute to the sigma bonds because it's sp2 hybridization. Okay, so in this video I've shown you how to calculate the band structure of graphene and what is the orbital contribution of the different bands. If you learned something from my video, I really appreciate your like or subscribe to my channel, and I hope to see you next time.